The next measure is Logworth. Logworth works somewhat differently. So you don't have the left side Logworth and right side Logworth and take a weighted average. No, you don't have to do that. So for each split, you get one Logworth value. That's because you're considering all the splits at the same time. So in case of binary split, so you'll have the left side split here and the right side split, only two branches. Okay, in case of more than two branches, so here I'm giving an example of three-way split. So you have three branches, and then you have the target level. So in case of binary target, you'll have only two columns. So how many in the first split, the first branch, how many level 1 and how many level 2, and then same for the second one, middle branch, and then the right side branch. Okay, here if you have three possible levels for the target, then you have how many or level, you take the leftmost branch, how many are level 1, how many are level 2, how many are level 3, and then repeat that for the middle branch, repeat that for the rightmost branch. So you construct a table like this of observed frequencies. So you're considering all the branches at the same time. Now we're going to use what is called the chi-square test, which is a test of independence. Okay, if the target levels are completely independent of the branches, so then that means this is impure, because they are, if they follow a particular pattern, then it will be pure. Like if all level 1 is here, and all level 2 is here, all level 3 is here, that means it's perfectly correlating with the split, in which case there is complete dependence. You know where if it is split 1, then target is level 1. You can tell that if it is, if you have completely pure split. So in that case, well, let's have that on one hand. Now you compute what is called expected frequencies, and these expected frequencies give us expected frequencies when the split is completely impure. Because if it is completely independent, okay, there is no purity at all, then this is what you will see. So to the extent these deviate from this, okay, if these are way different from this, then the observed frequencies are pure, relatively speaking, to the completely impure situation. So you find the expected frequencies, that is, you find the total for each row, total for each column, and then you multiply row I total with row J, column J total, and then divide by n is the sum of all the observations, total number of observations. So once you have that, once you have the expected frequencies calculated, then you put them together into this formula. Okay, so that gives you chi-squared stat, and then you find the p-value using this function in Excel. Okay, so you have the chi-squared stat, comma degrees of freedom. The degrees of freedom is given by r minus 1 times c minus 1. R minus 1, r being the number of rows, c being number of columns. So you find the degrees of freedom in this way and plug that in, and you get your p-value. And this p-value will be, to the extent that we have a really pure split, the p-value will be really, really small, because your chi-squared will be large and p-value will be small. So when you have really small p-values, it becomes very hard to compare one split against another when the p-values are small. So you use the p-value into a logarithm with a negative sign, so that's what is Logworth. So what happens is it has the opposite. So for smaller the p-value, the larger will be the Logworth. So the more purer the split, the larger will be the Logworth. Okay. As the Logworth increases, the purity increases. So when you use Logworth as the criterion for selecting your candidate split, then you must select the one with the largest Logworth. We'll look at a numerical example of this in Excel.